All right, so 2.11, we're graphing logarithmic functions. The easiest way to graph logarithmic functions is to do the exponential function and then swap it over y equals x. So if we think about some characteristics of log functions, we talked about this a little bit last class. A can't be 0 and b can't equal 1. The domain, why do we think the domain would be from 0 to infinity? If we look at the graphs, what's happening at x equals 0? Jordan?
Is it a vertical asymptote?
Yes, there's a vertical asymptote at x equals 0. Just like in exponentials, there was a horizontal asymptote at y equals 0. So the range for exponentials was 0 to infinity. For logs, the domain's going to be 0 to infinity. And then the range, so we got 0 to infinity because of the vertical asymptote. And then the range is going down negative for y. And even though it kind of looks like it might be like petering off a little bit, it is increasing. It's just increasing really slowly forever. So it's like kind of getting bigger and bigger, just taking its time. So the domain, the range is negative infinity, positive infinity. If a is positive, then it's going to kind of look like a square root graph with a tail. And then if it's a is negative, that means it's reflecting about the x-axis. What?
What do you mean by reflecting about the x-axis?
So originally the graph, when we were going like close to x equals 0, the y's were going to negative infinity. So we're reflecting this, everything flips over the x-axis. So now as we're going to 0, instead of going to negative infinity, the y's are going to positive infinity. They're doing like the opposite. We're not going to deal with negative b values. That's not really a lot, like just how we didn't have negative b values for exponentials, because when we had negative b values in exponentials, it would zigzag the graph, bigger and bigger and bigger, or smaller and smaller and smaller. We're not going to have negative b values for logs either, because that would do crazy things. So as we're looking at the first graph, let's talk about increasing versus decreasing. Is there any change on the left graph with its increasing or decreasing? No. So because there's no change on increasing or decreasing, what does that mean there's not going to be? Maximums or minimums. Remember, functions have maximums or minimums, extrema, when the function changes from increasing to decreasing or vice versa. So logs have no maxes or mins. And then concavity. There's no points of inflection because there's no change in concavity. They're either always concave up or always concave down. So looking at the graph on the left, I would describe this as being always increasing and always concave down. And let's just remember, when a function is concave down, what does that imply about its rate of change? Good, the rate of change is decreasing. The graph on the right is always increasing or decreasing? Decreasing. It's always decreasing. Remember, when we're talking about increasing or decreasing, we're reading it from left to right. So the graph is decreasing as the x's are increasing. So the y's are always decreasing and concave up. So when something's concave up, its rate of changes are increasing. I'm reminding you of your increasing and decreasing because one, I think it's something you need to remember, but also Miss Daly on this morning was talking about how glad she is that the kids take AP Precalc where we talk about concavity and increasing, because that's what she's teaching right now in calculus, and how much better the students understand that now that we talk about it in Precalc. So, hey, nice little shout out from the calculus teachers. All right, the end behavior of log functions. For log functions in general, as an input increases, the output will either increase or decrease without bound. Without bound means it's going to infinity. Since the log has a domain restriction at the vertical asymptote, the end behavior for the left side of a log will have 0 plus. Remember, the 0 plus means that as x approaches, zero from the right, or like the more positive side of it. And it's of the vertical asymptote. So it's approaching the right side of 0. Plus is on the right side because that's where more positive things are. A minus in the, like 0 minus, means from the left side because that's where more of the negative things are. The end behavior for a log statement. Notice that the y's, like we said, will always be increasing or decreasing without bound for both of them. So it's a pretty safe bet if I'm asking you to write the limit statement for a log that you're going to either put a positive or a negative infinity. You're not going to put any other kind of number. So like put 1, take a guess if you don't know. It's the left limit will always be at 0 plus or whatever the vertical asymptote is. So how we find if it's a shifted vertical asymptote is the transformation form for a log. Looks like that. And if we have a vertical asymptote, A, B, H, or K, which of those things do you think is taking an x equals 0 and shifting it horizontally left and right? H. So the H is how we are shifting our vertical asymptote to whatever x equals H would be. So if you have like log y equals log 3 of x minus 5, your left limit behavior would be x approaches 5 from the right. Because that's the vertical asymptote shift. Okay, try looking at the graphs of these. Try to write your limit behavior for the left and the right limit. Okay, so on A, the A value in front of whatever log this is would have to be positive because it's growing forever. So what would F be approaching on the left side? JJ, what do you think it's approaching on the left side of 0? Or, Negative infinity. On the right side of 0, but the left limit is what I meant to say. All right, Valentina, how about the right side? Positive infinity. And the x's are approaching also positive infinity. For the left side of B, Patrick, what are the x values approaching on B? The values are approaching positive infinity, but I meant what is that limit x approaching on like the little bottom? 0 plus. Don't forget to put the little plus. And then the right side, Angus.
Approaching negative infinity.
Okay, the y's are approaching negative infinity as x is approaching positive infinity. And then C does not have, and A would have been negative on this graph because it would have reflected it. C does not have a graph. I would strongly encourage you, as you're trying to get better at recognizing these, to sketch a little graph. So A is positive. Which one, A or B, does this graph look like? A. So it looks like A. You can get a little, if you want to graph it that way too. Wow, super beautiful to scale graphing I did there. So approaching 0 from the right, G would be approaching. Austin, what do you think? Good. And then x approaching positive infinity. Jacob, what do you think G is approaching?
Positive infinity.
Good. All right, flipping over. Example 2 is talking about increasing and decreasing in concavity. Circle the ones that you think are appropriate for each of the graphs. All right, for 2A, Janaya, what is it? Concave up and decreasing. Correct. 2B, Z. Concave down and increasing. Good. And Graham, 2C. Concave up and decreasing. So 2A and 2C should have similar looking graphs with each other. Okay, good job. Hopefully that was feeling like we know what we're doing a little bit there. Now let's look at, also, I think you might notice this, but anyone notice something about the relationship between increasing and concave up and decreasing concave up? I said that backwards. Concave up and decreasing. Those are together, right? So if it's concave up, the function should be decreasing if it's a log. If it's concave down, then it's increasing. And vice versa. If it's increasing, it should be concave down. Because that's just how logs will look every single time. You got a 50-50 shot to get it right, I guess. All right, example 7. This is what we did last class. Select the selected values of a function. Of log functions are shown below. For each table, find the value of k, which is like the missing thing. We're not going to do these two, just so you know. Well, I guess we could, but we got a lot to do today. Let's just do these two. Okay, so they told us that these are log functions. What do we know? If we have a table, what do we know about log functions? Carolina?
The x's are either going to be increasing or decreasing like y's in an exponential function.
Say it again.
Okay, so like if the x's are going to be either increasing or decreasing like y's in an exponential.
Okay, like the y's in the exponential function, which means what? What are we looking for the x's to have happening? Multiplication. So the x's, or the inputs, are having some kind of like multiplication by the same number. So you can tell what's happening. You know that x is being multiplied by the same number each time. What was 1 multiplied by to get to 2? 2. Just confirming that we're right. What was 8 multiplied by to get to 16? 2. So then we have to multiply 2 by 2 to get to k. 2 times 2 is 4. And then you're like, did I do that right? 4 times 2, is it 8? Yes, it is. Yay. And now we're going to work our way backwards. What times 6 got you to 18? 3. And confirming 3 times 18 is also 54. So what times 3 is 6? 2. These over here have like shifts vertically. I'm not going to do that to you. So we're moving on to example 3, talking about domain. In the domain, find the domain and range. If you want to flip to the last page, the range is always something. What is the range always for logs? Yes. Or you could put all real numbers if you want. However, the domain is a little bit more complicated. The way you find the domain for logs will be in the form log, and then this is called the argument. The argument is whatever the parent function is happening to. So even if it's like a square root, the thing that's being square root is called the radicand, but it's also called the argument. So the argument of the log is the thing that the log is happening to. You want to get that argument, the domain of the argument. Is there an E after the U in argument? You say, I don't know. Come on, communications major. The argument. I think I did that. Is there a U there? Or an E after the U? What do we think? No? Yes? No? Nobody knows? No. Okay, thank you. Argument is greater than 0. So let's look at, well, A is easy. Here's the argument. So we're saying x is the argument, make it be greater than 0. I didn't have to add, subtract, multiply, or divide to solve for x. So my domain is everything bigger than 0. If you have an inequality and you're not sure how to put it in set notation, interval notation is what I meant, graph it. So I have an open circle because it's not equals to, because we can't log 0. That's where the vertical asymptote is. We can't have an equals to there because there's a vertical asymptote at x equals 0. You graph your inequality. If the x is on the left side of the inequality, it's pointing to the direction where you need a shade. And now you can do the interval notation nicely because it's like you read interval notation from left to right. So the leftist thing would be 0 and the rightist thing would be infinity. And both are not equals to, so both have parentheses. So on B, the argument is x minus 3. X minus 3 has to be greater than 0. solve for x. X has to be greater than 3. So what do we think the domain's going to be for this one, Sienna? Yes. All right, C is a little bit more complicated. You got to subtract and divide. All right, we have an inequality and there's a negative here. When I divide, I'm dividing both sides by what? The negative or the positive? What number am I dividing to solve for x? Positive 2. So do I need to switch the sign of the inequality if I just divided by a positive number? No, you do not flip the sign. A lot of people get like, oh, I see a negative's involved and it's an inequality. I don't know what to do. When you flip the sign is if I had like 5 minus 2x greater than 0. The fact that the 5 is negative doesn't matter. It's the fact that you're dividing both sides because you're taking something where you're saying the x values were originally bigger than this negative number. And then dividing both sides by negative 2, you have flipped from having that x value being bigger than some negative number to now you need to realize that this is now a positive number. It's completely changing the sign. It's like flipping the orientation of the number line for this x value. So you have to flip the fraction or the inequality over. Yep.
For like next to -3, should be like a bracket or like
Parentheses, because we're not gonna, this is the vertical asymptote, so we can't equal the vertical asymptote. All right, let's go to 2.12. Sort of just as snappy of a lesson. It's either AII or AI, I'm not really sure, but AI, artificial intelligence. It's always about manipulating logs. So this is not something that goes away. You did do this in Algebra 2. It's one of the things in algebra, theoretically, it's one of the things in Algebra 2 that I think people struggle the most with, is the properties of logs. What do we know about logs and their relationship with exponents? Carolina? They're inverses of each other. So they have, when I deal with an exponent, I'm going to deal with it the same way as I do with a log. So thinking here, if I had an exponential form, log m times x to the m times x to the n, what would you do, because they have the same base, what would you do with those exponents? Add them. So when I see log something times something, it should become a plus sign when I want to separate them. Do you see how the plus sign brought the bases together in exponential? Logs are inverses of exponentials, so it's going to separate them. The plus sign will spread them apart into two separate bases. So anytime you see a log plus a log, you need to think, what's a more powerful operation that makes the numbers get bigger. So I see a plus sign, and if I want to go to a single log, I have to go more powerful operation that makes numbers get bigger, typically. So what makes numbers get bigger that's more powerful than addition? Multiplication. And you can take your plus sign and turn it on the side, and look, it looks like a multiplication sign. Oh, it's lagging like crazy. Quotient property. So I'm thinking like x to the m over x to the n. What would you do with the exponents? Subtract them. So again, in exponents, to get a single base, you used subtraction. In logs, it's the opposite. When you have subtraction, that's making there be two bases. A single base, you have to go to the more powerful operation. So with logs, when we see a minus sign, we think of the more powerful operation that would make numbers get smaller, which is division. Also, they both look the same, right? Like a little line. Then we have the power property, and I think the power property is the most confusing one for a lot of people. So in the power property, you do x to the m raised to the nth power. What are you going to do with m and n? Multiply them. It's not as obvious, but if I have an exponent in log, I'm bringing it down in front, or I can go back up top and do multiplication in front of the log with that exponent. Yep.
Why in the example for the quotient property is there?
That's a typo. Thank you. Another thing that I do want to point out is that division is just actually multiplication, just like subtraction is addition. So with division, you could also take this property of logs, like why the division works. If I have log base 10, or I guess it was b in this case, but who cares, minus log y, I can use that power property. What's multiplying the front of the second log? Yeah, -1. So I can move the -1 into the exponent. So really now I have log x plus log y to the -1. And what does something being raised to the -1 power do? What does it do? It flips it as a fraction. So you're going to have log x plus log 1 over y. Now, how can I condense? I have log x plus sign log y. I want one log. What operation has to be happening between x and 1 over y? Multiplication. So you're going to have x times 1 over y, which we could write as x over y. It's way longer to do it that way. That's why someone came up with the quotient property. But the quotient property is doing the power property and then the multiplication property. Well, let's try to do, the thing that's on the AP exam is almost always going to be something like example 1. So using a property of log, it's usually like 1e. I think it's like they kind of need you to know how to do things. But let's do A. We're going to build our way to E. So doing 1a, what sign do you see between the two logs? A plus. So, my single logs. We got to write it as a single log. Please don't put a plus in between the x and the y. I will lose my mind. What are we going to put between the x and the y? Multiplication or nothing. You could put a little dot if you want. You could put parentheses, whatever. Try to do B. All right, what do we think we're going to put for B, Allie? Perfect. Okay, then A and B. Any questions on A and B? Because I think in order for you to do anything else, you need to understand how to do A and B. All right, give me a head nod if you feel like you know what's going on. Thank you. Okay. Well, some of us didn't nod our heads very much. I'm a little worried. Oh. Oops. Everything we've done this year, you did in Algebra 2. So technically you've learned this already. Oh boy. Okay. Well, on C, this is the thing that people will mess up. When we have two minus signs, here's what I don't want you to write. I don't want fraction, right? A fraction and a fraction is not good. We don't leave, in math, you're not allowed to leave a fraction divided by a fraction. What you could do is say, well, this is the numerator, and my denominator would be z over 1. Well, I can multiply by the reciprocal, but that seems like a heck of a lot more work. So instead of doing that, I want to explain why the 5 and the z are definitely going to be in the denominator, is because we could factor out a negative from both the log 5 and the log z. If there's a 10 in the base, you don't need to write it. It's an implied, the common log. Now, what is happening between the log and the z if I want to write it as a single log? Multiplication. So I'm going to have 5z. Then you have log x minus log 5z. What's going to happen between those logs when I want to write it as a single, or not between those logs, but between those terms, arguments of logs? If there's a minus sign. Division. And it goes in order, just like exponentials went in order of like top minus bottom. Same thing. If it's whatever's positive, where did it go? Whatever's positive, the x is positive, it needs to be in the numerator. And the 5z is with the negative log, so it should go in the denominator. Okay, that seems like a lot of work. What you could just realize is that anything that has a negative in front of it, any log with a negative, the thing that is being logged is going to be in the denominator. So way more simple if you just realize, oh, there's a negative, 5 and z, they're going to both be in the denominator. They must be multiplying each other in the denominator. Okay, but the reason why they're multiplying is because you factor out the negative and then it becomes a plus and they're multiplying in the denominator. Okay, try to do D. This is new-ish. What are you going to do with the 3? Because we can't condense at logs if there's a number in the front of it. You have to do something with the 3 before you can condense the 2 logs. And what do you think you have to do, Ola? What's the end? What do you have to do? Make the 3 the exponent for x. you were looking like you were done because you were just sitting there like a bum on a log, so that's why I called on you. I didn't really think so we have to make the 3 be the exponent for the x. So you have to do this first. You can't condense logs if there's a number in front of the log. And now what are you going to do between x cubed and y, Patrick? What do we do if there's a minus sign between logs, Patrick? Okay, so I'm going to divide x cubed and y. Yep. All right, D is more like it. This is combining. Your powers combined. It's like the Captain America. Oh my gosh, do you guys know who not Captain America, Captain Planet is who I was thinking. Do you guys even know who Captain Planet is? He's like green-faced. Yes. Heart, earth, wind, fire. I'm missing one. And then they put their little rings together. And they save the planet from like pollution. And there's like a catchy theme song. Come on. Oh my gosh. What was your PBS childhood? Clearly not PBS enough. Only JJ knows. All right. So we have to move the 2 and the 5 up first before we can do anything else. So make it be, the 2 is only the exponent for A. The 5 is only the exponent for B. And 4, the log didn't have anything in front of the 4. We can rearrange the logs. Commutative property of addition says you can rearrange these. If it's going to confuse you, you can put this plus sign log next to the other positive log. It's just commutative property of addition. 3 plus 2 is equal to 2 plus 3. Negative log 7 b to the 5th plus log 7 4 is equal to log 7 4 of negative log 7 b to the 5th. Now I think it's a little bit more clear how to do this. We want to write it as a single log. What is going to be in the numerator for the single log, Lucy? 4a squared. I feel like process of elimination. Nat, what's going to be in the denominator? Thanks, Nat. He really got good at ventriloquism and threw his voice over there. So we got the b to the 5th because it came after the minus sign. So after a minus sign, this thing's going to be in the denominator. Okay, F is another cutesy problem. There's just a number with a 2. I'm going to give it some stars too. I love this one. F is not for fail, it's for favorite. So what property, we learned this the first section when we did logs, so 2.9. How do I cancel out a log? How do I, if I have, or an exponent or whatever, what log base what of what would equal 1? Yes, so if it was log base b of b, it equals 1. So looking, Carolina said it, we have a 6 down here. So we have to use a fancy form of 1 for logs. This 2 needs to be multiplying log base 6 of 6, because that's a fancy 1. questions on where the log base 6 of 6 came from. Again, this 2 here times 1. This is 1. Because we have to condense these to a single log. So we need to be able to have that to have a log with it. Okay, so now what am I going to do to condense these to a single log? What's the first thing that has to happen? Move the 2 up. Are they ready to condense now? Was that yes with a yawn? Okay. And the 6 squared, let's rewrite that as 36 times x. All right. Now on to expanding logs. Expanding logs is not usually a free response question. It's usually more a multiple choice type question. So if I had to expand this log, we had to get it fully expanded. So no exponents with it. So the first thing I'm going to do is first, let's count how many terms we have. 2 terms. The exponent is not its own term. We have x squared and we have y. So we have 2 terms. If we have 2 terms, that tells us how many logs we're going to need. So if we have 2 terms, we need to write 2 logs. I guess log base 3s, but whatever. We got log base 3. Log base 3. We read left to right, top to bottom. So the first thing we're writing is an x squared and then a y. What sign should go between the x squared and the log y? Minus. Perfect. This is not completely expanded. There's one more thing you can do. Jordan.
Do we have to change the exponent to 2 times the log base?
Good. Yes. Okay, checking our answer. C. And then, second, I guess the last thing we need to do. Now we're talking, just like we did with exponentials, we can make logs look like different functions using the properties of logs. So right now, how would you describe the 6 inside with x, it's multiplying x, what kind of transformation is this? I know, but are we reading? What kind of transformation is it? Horizontal dilation of what?
Oh, the function.
No. What factor? Sorry.
6.
No.
No.
1/6.
Oh, the 7.
Yes, because it's inside with x, has to do the opposite operation, so it needs to be dividing by 6. All right, the function, so it's a dilation of the function log. Show that f can also have a vertical translation using properties of logs. So how would we expand log 6x? First question I should have asked is how many terms do you see? Good. 6 and x are 2 different terms. And that's usually what people mess up with properties of logs when you go to expand, if there's a coefficient of a variable, you think that that's like married to the variable for some reason, and it's not. There's multiplication happening between the 6 and the x. So there's two terms. That means we can have two logs. Marielle, what's going to go in the first log? She could have said either one. I would have said okay. And then the second log would have been x. This log x is g. This is like what's translating. If we look over here, this is g. This is the thing that's a function of x. And then log 6 is a number. It's a constant. It's something that you could type in your calculator and be like, oh, that's 1 point something. I don't really know what log 6 is, but it's something like that. 10 to the x equals 6 is going to be little. So this is just like another application of the properties of logs. I definitely have a question like this on the semester exam, just so you know. Looking at the change of base. The change of base formula, with the invention of your calculator being able to do log base and Desmos being able to do log base, is kind of seen as passe. Like, it's a little bit like, why are we still caring about this? The only reason I can give you is because on the exam writers decided they still cared about the change of base. So I guess I'll care about the change of base. But it's not super, it's kind of cool because if you need to change something from like logs to ln's, the change of base comes into handy. But basically the change of base is log of the big number. We'll call this big. It's like font size big. Not numerically bigger, but like its font size needs to be bigger. And then we'll call this the base because it's the base. So when you do the change of base, you do log of the big over log of the base. And A can be anything. So A can be, so if you're, this is also like in a lot of math competitions. So in like math competitions, they do the change of base a lot and you can make it be whatever you need it to be. So if you need it to be an ln, log base E, you could say ln x over ln b. Looking at example 4, we have log base 4 is f and log base 9 is g. We want to show a vertical dilation of g by finding a value that's a constant such that f is equal to k times g. This is very complicated wording, but here we go. We're trying to go from base 4 to g of x, which is base 9. So we're rewriting f. Log of the big is going to be x. Log of the base is going to be 4. And what log base number should I make them have, both in the numerator and denominator, so that it becomes a log base 9? A 9. You can be done. But this is g of x. And so sometimes they'll just ask you, like, what is the value of k? And a lot of people would say log base 9 of 4. The value of k is not log base 9 of 4. What is log base 9 of 4 doing to g? It's dividing it. So it's really 1 over log base 9 of 4. times log 9x. This is g, and 1 over log 9 of 4 is k. And now we have it in the form k times g. And just as way of reminding you, the natural log, ln, is log base e. We've done this already, but just so we know. So a log with a base of e is called a natural logarithm. Which of the following is equivalent? So this is just using the same, if it's an ln versus a log, they are the same thing. It's just trying to reaffirm that ln is log base e. But what do we need to do first in this problem? Are we going to divide those x and y? No, we cannot. Yeah, we're going to put the exponents up first. We have ln x cubed minus ln y to the 4th. Because if you divided the x and the y first, what would you be doing with the 3 and the 4? Would you be dividing them? Would you be subtracting them? Like, we don't know. So move them first. And now, what's going to be in the numerator? X or y? X, and then the y is in the denominator. So is it b? No, that would be multiplying them instead of being the exponents. No. Is it c? No. To get a single log when there's minus in between, you have to do division. Same thing, and this is like double bad on D. No. But definitely A, as in also. All right, so looking at our classwork, we are going to do... Uh-oh, I lost the paper where I marked which ones I wanted you to do. Oh, okay. So if we're looking at 211, so pull out 211. We're doing 2, 5 through 7. I mean 4 through 7, my bad. That whole like left side of the chart. And then flip to the back. 14, 16. And I want to go over 16 real quick because I have a feeling a lot of us are going to do 16 incorrectly. So in 16b, I'll do with you. Okay, it's asking for the domain and the range. We know that the range is going to be negative infinity to positive infinity for all of those, so you could just write that in. But what B is asking is not if the log was shifted to the right 3. What this is asking is if it was just like originally shifted to the right 3. It's saying for G, in this transformation, where you see the x's, where x is, you're going to subtract, have x minus 3. It's really 3 log base 5, x minus 3 plus 4. It's shifting it to the right 3. So what's actually being logged? X plus 1. And then do the domain for that log. The domain for x plus 1 would be take that part, make it greater than 0, solve for x. I don't want to do the whole problem for you, but you're basically there. All right, then we're looking at 12. I feel like you'll really get the gist of it, but because I'm worried some of our friends did not get a great grasp of this, 1 through 6. Please help each other. This is something that people struggle so much with, and some of you intuitively understand it and some of you do not. So please help one another do this. And then we're going to do 8, 9, 11, 12, and 13. Okay, so again, that's 1 through 6, 8, 9, and 11 through 13. And on the other worksheet, it was 2, 4 through 7, 14, and 16. Hopefully most of these are pretty quick, especially on 211, but